we start, I'd like to give a small introduction. So, Javier Morán Fraile, is that okay?
Yes.
Yeah, my Spanish not that good, but yeah. Is visiting us this week, and he does magnetohydrodynamic simulations of mergers between compact objects. And today he's going to present something mainly about white dwarfs, I guess, but maybe you will mention some neutron stars as well.
Yeah.
And I think this is of relevance to many people here at IvS. And so to give a little bit of history, Javier originally comes from Spain, did his bachelor's there, and then did his master's in Amsterdam before moving to do his PhD in Heidelberg at the Heidelberg Institute of Theoretical Studies. Currently he's a postdoc there, and then there's potential for him to come here. And so, yeah, I think he does really exciting simulations. And here in particular for the white dwarf mergers, there's this very interesting connection to type 1a supernovae that he will talk to us a little bit more about today. So Javier, the floor is yours.
Thank you very much, Eva. So as Eva has mentioned, my work revolves mainly about 3D simulations of stellar binary interactions. So today I'm basically going to talk about some of my most recent work, but at the same time, this is kind of going to be a showcase of what you can do nowadays with 3D MHD simulations of compact object interactions, showing several different things. So I'll go a bit all over the place, so if something is not clear at some point, you can ask questions. This is also meant to show many different things, because as Eva mentioned, potentially I will start working here, so it's interesting if people know what I do and if we can find interesting avenues for collaborations. So one of my main interests is, can I guess word? Yes, compact object mergers. So I think these events are fascinating on its own, but it's also pretty clear that they're extremely important for astronomy and for physics, even for physics in general. So we know that compact object mergers play key parts on the nucleosynthesis of the universe. We cannot explain some of the metallicities that we observe without the role that compact object mergers play. They also produce a myriad of different transients, some of the brightest ones as well. We know that type 1a, kilonova, GRBs, all of these are most likely produced by compact objects at their interactions. And they're able to produce these extremely bright transients because these events are some of the most energetic ones that we know. And this means that these events can give us access to regimes of density, temperature, gravity that are just simply not accessible in labs. We cannot reach these conditions that we find in these objects anywhere else. So if we have accurate modeling for these events, we will be able to even probe physics that otherwise we cannot know. For example, like the equation of state of neutron stars, all of this stuff, we need accurate models to be able to probe these regimes. But at the same time, being this energetic, these events are extremely challenging to model. We have so many different physics acting on many different scales. We have the interplay of nuclear reactions, magnetic fields, gravity, all of these acting at different timescales. And we have some of these processes that are inherently three-dimensional. So simple modeling like 1D or analytical prescriptions sometimes are not going to be enough. And in my biased opinion, 3D simulations provide the best description of these events. In particular, I'm interested in some compact object mergers that have received less love from the 3D modeling community, such as neutron star white dwarf mergers, why I'm not here, neutron star white dwarf mergers, or low mass binary white dwarf mergers. But before I move on to these results, a very brief explanation on methods. So most of the simulations that I perform are with the code arepo, which is a pretty special code. So it's a 3D MHD code, which itself is not that special nowadays. There are tens of 3D MHD codes. But what makes arepo so special is that it uses, instead of a fixed grid or a fully Lagrangian formalism, it uses a moving mesh approach, an unstructured moving mesh approach, which makes it combine the best of both worlds. So it makes it perform extremely well for binaries in particular and mergers. One of the neat features of arepo is that this mesh can be automatically and continuously refined so that we pour resolution where we want it and only when we want it. And this allows to free computational resources by just not having resolution where we need it, and just putting it explicitly where we need it. Another nice feature of a repo is that it can be coupled to nuclear reactions, so we can also simulate interactions where nuclear reactions on dynamical timescales are important, such as type 1a supernova or anything with relevant burning around a white dwarf, for example. So let's move on to the first system that I want to discuss today, which are neutron star white dwarf binaries. So depending on who you ask, these are second or the third most common type of double compact object after white dwarf binaries, depending on how many black holes and neutron stars you form. So we expect that there's around 1 million of them just in the galaxy, but still they're not as studied as neutron star mergers, for example. We know they exist. We know they should be sources of gravitational waves in the LISA frequency band, so we will start seeing them when we have LISA. And as their orbits shrink due to gravitational wave release, they will eventually start interacting. Depending on the mass ratio between the white dwarf and the neutron star, we may have stable mass transfer and lead to the formation of ultra-compact S-ray binaries. Or if we have a mass ratio over a critical value, this will lead to a merger. And this is the case that I'm interested in because the outcome of these mergers is not that clear. They have been proposed to have many different types of outcomes. It could be the explanation for the formation of magnetars. Depending on how much material is accreted onto a neutron star, you could form black holes. They could give rise to, they have been proposed to give rise to different types of transients, ranging from long GRBs to fast radio bursts to fast blue optical transients, many more. But the thing is, how come being this event so interesting, so mysterious, having so many potential outcomes, have not been studied that much? And the thing is, numerically, these systems are some of the most challenging to simulate. As compact mergers, these are among, I think, arguably the most difficult to simulate because they have a challenge that you don't have in mergers between white dwarfs or neutron stars or even neutron star black holes, which is that there is a vast range of special scales in particular. Because even though both are technically compact objects, they're not the same level of compactness. So neutron stars have radii in the order of 10 kilometers, whereas white dwarfs are close to the size of the Earth, over thousands of kilometers. And this means that they're going to have also different characteristics at timescales. Neutron stars have timescales in the order of 10 to the minus 5 seconds, whereas white dwarfs in the order of seconds, and their mergers are going to be in the order of hundreds of seconds. So if you want to simulate all of this in 3D in particular, you need to cover all this vast range of spatial and timescales, which has been traditionally out of scope for most 3D methods. For this reason, previous works have been resorting to tricks, such as scaling the white dwarfs down to the size of neutron stars, or using low-resolution SPH simulations to have first glimpses of how this looks like. But as I mentioned, our repo is pretty special, and we can go a couple of steps further. So thanks to that, last year, we performed the first ever 3D MHD simulation of a neutron star white dwarf merger. So this was published already a year and a half ago, I think. And we have many more simulations of this, but this is the one that we studied here, where we studied the merger between a 1 solar mass carbon-oxygen white dwarf with a 1.4 solar mass neutron star. So after bragging how special our repo is, I still say that there is a limitation, which is that we don't have infinite computing time, and I had to finish a PhD. So we had to put the neutron star as a point mass, so that this was able to be simulated in less than 4 or 5 years, So the neutron star will be a point mass and will be the main limitation of the simulation because we cannot model accretion into it properly. So despite we have the smallest cell size, say next to the neutron star being 20 kilometers, so we are not that far off in scales, we consider an area of around 800 kilometers around the neutron star as unresolved because we are missing the physics in the smallest scales. So this is a pretty high resolution simulation. The number of cells doesn't really tell you too much because the cells are different sizes everywhere, but this is a pretty high resolution simulation. Also another limitation, as the neutron star was a point mass, initially it cannot have magnetic field. So we give, to compensate a bit of a stronger magnetic field to the white dwarf to start. This is not super important, the actual value that is given. I can elaborate in that if anyone has questions later, but these are the initial conditions that we use. And in this particular simulation, we did not use nuclear reactions because most of the nuclear burning will take place in the unresolved area, and we didn't want to have to deal with these kind of worms for the paper. So we have simulations with nuclear reactions as well, and the overall picture doesn't change too much for what we're going to show. So let's look at how this looks like. I think the embedded movie is really choppy. Let's give it a try anyways. Yeah, I don't like this. Let's open it externally. 1 second. So here we have slices through the orbital plane. So we are seeing the system from the top. These are the initial conditions. As I didn't have magnetic fields around the neutron star, there is a plotting bug here, but ignore it for the beginning. So we have a white dwarf and a neutron star that is obviously point mass is invisible for now. So we're seeing from the top density and magnetic fields. Wait, if I do this, does it work? No. Okay. Oh, yeah, wait, that's, what? Okay, I'm confused. Okay, so as soon as the simulation starts, did it crash? That would be really nice. No, okay, it's just obeying me. Okay, so we initially start a simulation with the stars slightly further away from each other than the point of Rochelov overflow. This is to account for some tidal effects. And we artificially shrink the orbit for a couple of seconds until they start transferring mass. As you can see, the moment that we start a simulation, all the gas around the neutron star is going to start amplifying the magnetic field by many orders of magnitude, so it was not a big problem to not have magnetic fields around the neutron star. So we shrink the orbit a bit, and then when they start having proper mass transfer, we let it evolve freely from now on. And as you can see, the white dwarf transfers material to the neutron star, shrinking the orbit until the separation is short enough that the white dwarf is tidally disrupted around the neutron star and forming some sort of disk, which in real life is actually much more of a puffed toroidal structure. You will see it better later. And as you can see, the magnetic fields are amplified up to values of around 10 to the 13 in the neighborhood of neutron star, really, really quickly. This structure forms this disk super quickly, and we start having these periods of rapid accretion onto the neutron star, which is when we stop the simulation, because as we are not modeling the neutron star itself, this leads to some sort of problems. But just with this short timescale interaction, we already see very interesting things. So on the next movie that I probably also have to open externally, is this the same movie again? Yeah. Wait, how many times do I have this open? So here we have a 3D rendering of the same simulation, so that we can get a perspective of the scale. Why is the? Did we lose the brightness now? I don't know what's going on. Okay, whatever. So as you can see, the disruption of the white dwarf, this forms some sort of puffed up disk. But these super strong magnetic fields that we were observing give rise to these bipolar jet-like outflows, which we believe will be the main observational feature of this transient. So as you can see, also the structure of the accretion disk is not really like flat as a disk, it's more of a toroidal shape with these inspired features caused by the accretion onto the neutron star. But despite these 3D renderings being so interesting, they don't give that much information, so it's much better to look at 2D slices. So this is basically how the jet evolves. But okay, I'll live with the chopped movie. So here we're now seeing, again, the same plots as before, density and magnetic field from the top side, but now we have the radial velocity and the magnetic fields from the side. So as you can see, the moment that we start amplifying magnetic fields, when these jets start to be launched, okay, well. But the moment that the white dwarf is fully disrupted is when they start picking up speed, reaching velocities up to 10% the speed of light. That's the maximum velocity that we measure. And these jets turn on and off. They're not really symmetrical, which is perfectly normal. I think we have been observing jets like this already in the nature. But one of the main limitations that we'll have with this simulation, on top of not having a properly resolved neutron star, is that the resolution in the jets is not that great. In some parts, you can see that we don't have that many cells around, and this will have small implications on the parameters of the jet. So if we analyze the structure of the jet, for example, we can just look at the magnetic field lines. This is a 3D rendering of the magnetic field lines in the jet. You can see how the magnetic field coils around the neutron star following the accretion disk and then gets launched through the jet. We can also measure the estimated luminosity of the jet. So we know that, as you saw before in the movie, it turns on and off, so we have variability in the luminosity, but it's always in the order of 10 to the 40 ergs per second in the timescale that we simulate. And here is a summary of, I went too far, of the parameters that we measure in the jet. having maximal radial velocities of 10% speed of light, peak luminosities of 10 to the 47, a total energy release of 10 to the 49, but we have only simulated this small timescale with this opening angle and this mass ejection rate. But there are some shortcomings of this simulation. First, as we were not modeling the neutron star, the actual maximum speed of the velocity is a bit unconstrained. We expect higher maximum velocities if we resolve closer and closer to the neutron star. Also, the resolution in the jet is not that great. So from the preliminary tests that we have made, if we add more resolution to the jet, it becomes more collimated and faster. And this also becomes problematic because the simulation that we were having here did not include relativity, because for the distance that we were resolving around the neutron star, this was not a big issue. But the moment the jet becomes relativistic, this becomes a problem. So we don't want to give exact values for the jet, take all of this with a grain of salt, but we know that these systems will form jets, and this will probably be the most visible electromagnetic counterpart. What we have more confidence on is the gravitational wave signals released by these systems. So I implemented the computation of gravitational waves in a repo, and we can now obtain gravitational wave signals for all the mergers that we study. So as you can see here, this is the evolution of one of the polarizations of the gravitational waves. And it looks fairly similar to what you see in neutron stars or black holes. You have a shutdown after the merger. And in this case, we have some high-frequency components due to that you still have a remnant and you have mass movements around it. So we have only simulated this last 100 of seconds, 150 seconds before of the life of this system. So we're missing all the lower frequency components of the earlier stages. So here's, for example, the power spectrum of the simulation compared to the sensitivity curve of different gravitational wave detectors. And basically, this gray band over here, all of this is the signal that we are missing. That we know these binaries should be in the Lisa band, so we will probably be over here. But the merger itself will peak in the decihertz regime, which is unfortunate because we don't really have any, in the short term, we will not have any gravitational wave detector over there. We are in the regime between LIGO, Virgo, Cagra, and Lisa. So unless we get one of these really fancy decihertz observatories that nobody knows if they will ever see the light, we will not be able to detect the mergers themselves. But it would be really interesting to detect them because this would help us with multi-messenger astronomy identify properly the transients that these systems produce, because we know that they will be relatively bright transients. Just based on the hydrodynamics that we have performed, we some of my colleagues have speculated that this should give rise to some ultraviolet X-ray flashes resembling some fast blue optical transients. But at the same time, we're not modeling the neutron star, so we don't know exactly how much mass is accreted into it. And if it accretes into a black hole, the velocity of the jet will skyrocket, and this will potentially give rise to ultra-long GRVs. So we need more modeling for this. But at the same time, this is just the first baby steps in the world of neutron star white dwarf modeling. So we have some next steps that are pretty straightforward, which is improving a bit the modeling of a neutron star accretion and perform radiative transfer simulations of these jets to have a more accurate idea of how this would look like. So just want to get everyone excited in the field of neutron star white dwarf mergers. Hopefully, we'll have some new things soon. And then for the second type of transient that I wanted to mention today are the outcome of white dwarf mergers. So binary white dwarfs don't need that much introduction. These are arguably, without any discussion, the most common type of double compact object in the universe. We know they are targets of gravitational wave astronomy for Lisa as a binaries. And where the orbit shrinks and they start interacting, they will give rise to many different types of transients. The most spectacular one has been type 1a. And this has motivated most of the people to work on 3D simulations of most of the people that works on 3D simulations of white dwarfs has been focusing on type 1a, which is understandable. They are extremely interesting transients. They are really important for cosmology. They are really bright. They're really cool. But the problem is that to form type 1as, you need very massive white dwarfs. So there are many different proposed scenarios for the formation of type 1as, but most of them, if not all, involve carbon-acid white dwarfs with masses larger than 0.9 solar masses. But from what we know, as far as I'm concerned, most of the carbon-acid white dwarfs have masses around 0.6 solar masses. So we have a relatively large parameter space of white dwarf masses that are relatively unexplored, and could potentially be much more frequent than the interactions that lead to type 1a supernova. So that's what I have been working on the last years. In the last couple of years, this is a nice plot by Marius Dan with the landscape of white dwarf mergers. So we have the mass of one of the white dwarfs in the x-axis and the mass of the other one in the y-axis. Everything over here is just total mass over the Chandrasekhar limit, so all of these will end up exploding one way or another, most likely. And the current sub-Chandrasekhar progenitors for type 1a supernova are basically this corner over here, when you need masses larger than 0.9 solar masses. So we have all of this over here kind of unexplored, because we know, or at least expect, low mass white dwarfs will not lead to explosions. This one will lead to explosions, but the most frequent one are here in the intersection point. So what if we start analyzing this with detailed models? Can we find any transient here that could potentially be much more frequent than type 1as? So that's what I decided to do. And I started studying, for example, this is a setup that we published last year as well, where we studied the merger between a 0.6 solar mass carbonaceous white dwarf with a 0.4 solar mass helium white dwarf. So initially, we were analyzing this system as the result of a common envelope interaction. So for everyone that is not familiar with the common envelopes, it basically takes place when you have a red giant star that starts growing in size, engulfing its companion, and at this point, you have the companion and the core of the red giant orbiting in this common envelope, and the friction basically will make the orbit shrink until either the envelope is ejected or the core and the companion merge. So we initially were studying this system as a failed common envelope ejection, as a merger between the red giant core and its companion. But in the end, this, what you're going to see, should happen also if you have successfully ejected the envelope, if you have a stripped helium white dwarf with a carbonaceous white dwarf as a companion, and over millions of years, the orbital separation shrinking due to gravitational wave and merging, it should take place in a similar way. The important thing of this system is that the total mass was way below the Chandrasekhar limit. This is in the regime where most sane people would not expect anything interesting to happen on a short time scale. And this is due to the fact that the mass of the carbonaceous white dwarf is relatively low, and the helium that it would accrete should not burn on a short time scale. The higher the density, the two key things for people not familiar with type 1as or nuclear burning in this sense, helium burns much easier than carbon or oxygen, so if you have a really massive carbonaceous white dwarf and you start creating helium on its surface, the density is going to be enough to burn it. But at these low masses, we don't really expect anything to happen on short time scales. But this is not what we saw. If we now show another movie, can I open it directly? No, okay. So here we have now, with different color maps to make this more complicated, density and temperature, seen again from the top of the orbital plane. Again, we start with the white dwarfs far away from each other, and then artificially shrink the orbit until mass transfer starts. Where's my mouse? Yes, here. Okay. So the larger one is the more fluffy helium white dwarf that will start accreting onto the carbonaceous white dwarf. And as you can see already in the surface of the carbonaceous white dwarf, we are heating up, but there's nothing crazy happening. There's not that much burning taking place. But to our surprise, after the disruption, again, things heat up, but we observed that this ended up exploding. So this was super interesting, super fascinating, but at the same time, this meant a lot of work, because why is this now exploding? This was a regime where nobody expected these things to explode. What is going on? So we had to start analyzing in detail this simulation. So if we make a close-up of the, can I, please? Okay. Okay, yes. Wait. What if I press play here? No, it's still open, it's in my screen. Okay, never mind. So this is a close-up seconds before the explosion. Now we're looking at here at the kinetic pressure instead of the density, because the density doesn't really show you anything. So this is seconds before the explosion. What we are observing here in temperature is the carbonaceous white dwarf that has been completely engulfed in helium. So you have something that cannot really burn, engulfed in something that burns much easier, but still is not hot enough to ignite. And what we have observed is that accretion is not this picture of idealized material slowly getting deposited into the surface of an object, but it can be a 3D phenomenon with a lot of turbulence. So what we observe is this blob over here It's just inhomogeneities within the accretion stream. So basically, generate vortex, the trap material, and generate overdensities. And this overdensity, before being fully accreted onto the carbonaceous white dwarf, is just shearing on its surface, compressing, and heating the material. And this compression generates enough temperature to start a runaway burning of helium. So here, at this point on, we have a detonation of helium that is propagating around the shell, all the helium that is surrounding the carbonaceous white dwarf, burning around it and sending shocks inside the carbonaceous white dwarf. But still, these shocks that you can see are propagating through the interior are not hot enough to really burn carbon still. Like, this carbon is hot, but it's not burning. But the convergence of these shocks compresses the carbon enough to trigger the runaway burning of carbon and triggering a thermonuclear explosion that completely unbinds the carbonaceous white dwarf. So the takeaway point from this is that these mergers are so dynamical and chaotic in nature that without proper modeling, we may be missing some interesting transients. So itself, this double explosion, double detonation mechanism is not new. This is something that was known for, well, predicted for type 1a supernova, this mechanism, but it has never been expected to work in low mass white dwarfs. And also it has never been consistently ignited. So we may have more of these interesting transients if we just start analyzing them in detail. So the first thing that we did after knowing this is to check that this was not a one-off, that we did not have a super quirky mass combination where this takes place. So we perform small variations of the masses and more simulations of this. I don't know when the movie is black, this is really dark, but so we made small variations of the masses, perform similar simulations, and in all of them, like this, the mass range is relatively narrow. As you can see, we only changed 10% the mass of the carbonaceous white dwarf. And in all of them, we observed similar thing, the formation of an overdensity that ended up triggering a double detonation. So, well, all of them exploded yet? Not yet, okay. Yes. So now we believe that this mechanism is pretty consistent, but we still don't know exactly at which mass ranges this takes place. Because we know that if we increase the mass of the carbonaceous white dwarf a lot, this will not happen. If we decrease the mass, it also doesn't happen. So this will happen in a relatively narrow mass range. And before I move on to how this looks, well, sorry. Yeah, so before moving on to boring detonation physics and I lose everyone, I'm gonna briefly go over how this looks like. So we perform radiative transfer simulations of this afterwards. First, we looked at the yields that we observed because we were running this with the nuclear reactions. So the highlights are, we have a lot of helium as expected. This was a really massive helium white dwarf. We produce a very low amount of nickel-56, like less than a percent of a solar mass, so this could not power a type 1a supernova. The transient that would result from this will be fainter than a type 1a supernova. Other interesting feature is that it has a relatively high yield of calcium. The total explosion is similar to a type energy releasing the explosion is similar to a type 1a supernova, but that is not translating to too many things. But if you remember, we were studying this as potentially the outcome of a common envelope ejection or in isolation. So my colleagues have performed radiative transfer simulations of both these scenarios because they would give rise to completely different transients. So if this takes place inside a common envelope, why can I? If this happens inside a common envelope ejection, my colleague Sasako Sireva has basically put this ejecta ramming into a hydrogen envelope, and depending on exactly how the envelope is configured, how late in the ejection this takes place, it will look slightly different. But the overall idea is that this ejecta ramming into a hydrogen envelope could power light curves that look exactly, well, very similar to type 2 supernova light curves. So we cannot really say too much about, well, type 2s, as you know, normally are believed to be powered by core collapse. So it turns out if you have thermonuclear explosion inside of them, it could look relatively similar. We cannot give too much comparisons yet to specific objects because we don't have spectra yet. We're working on having a spectra for this case. And it would be nice to have rates in order to see if we can explain some quirky type 2 supernova with this phenomena, but we still don't have rates because we don't know exactly in which mass range this takes place. And also, this adds the complication of common envelope physics and when do they lead exactly to emerge and when not. So it's a bit more complicated. But we need to figure out these things, which we are working on in our group in Heidelberg. And in the case where this happens in isolation without a hydrogen envelope around it, we have much more information to give. So we have two papers on this right now. We have one from my colleague Fiontan Callan from last month in the archive, where they have performed NLTE, radiative transfer simulations of this explosion, where they have obtained spectra and light curves. I need to preface this by saying that I'm not an expert on at all on this, but from what they say, these are really good matches for this subclass of transient called calcium-rich transients, which some people claim that it's a subtype of type 1a because the light curves apparently are relatively similar, but much fainter, which it's matched really well by our low production of nickel. We have a much fainter transient. And as their name implies, calcium-rich transients have very strong peaks of calcium that we produce. So we're really happy with this, but we need to obtain rates for this in order to see if we can explain at least a subset of these calcium-rich transients, or all of them, who knows. So we're working on that as well now. So when there are two approaches for this, for figuring out the rates. One is to just make a parameter study of 3D simulations, which is very expensive. I'm partially doing it. But the other approach is to better understand when and why these systems explode, which is what I have been working on in the last year, more or less. So one of the main challenges that 3D simulations of explosions have is that the ignition of the detonation of the onset of the explosion takes place on very, very small scales. So, for example, for a helium ignition, this detonation takes place in scales of 100 meters, and for the carbonation ignition, the ignition takes place on scales of centimeters. So all the simulations of type 1a supernova, or my simulations, all the ones involving thermonuclear explosions, if they are 3D, they have an unresolved ignition. So this means that you have just a couple of cells where you have such a high density and temperature that you just trigger an explosion, but there is no continuity between nothing, supersonic detonation. And one may be asking themselves, is like, okay, but is this physical? If you have enough resolution in there, will this still be the case? So normally what it's been done in all the simulations, in all the 3D simulations, is to just compare to what the conditions that you find where it explodes with simulations of 1D ignitions, because in 1D you more or less, you can have it, you can resolve it, just that we don't know if this physics translate from 1D to 3D, so this is the best that we can do. To just check, for example, in the helium ignition, we measure, okay, this density, this temperature, our resolution is 90 kilometers, this would take place in 100 meters. But this would, in 1D, this leads to an explosion. Okay, fine. In carbonation ignition, we do the same. We measure density, temperature. In 1D, they say this explodes. Okay, let's hope that it does. But this is a big drawback of all 3D simulations of type 1a supernova. We have this uncertainty of whether or not this actually happens. So over the last year, I've basically been looking at this number, thinking that's not that unreasonable, like 100 meters. So I have been just pushing a repo to its limit, pretty much. And this is where all the bragging of all the flexibility of resolution of our repo comes. And I have just taken one of these explosions that I showed before, one of these models, and just as I know where the detonation takes place when it's unresolved, I can just decide to just add a lot of resolution there right before it explodes, like a couple of seconds before, a couple of seconds before it explodes. So this is a similar scenario, but we have managed to locally increase the resolution down to a level where we, for the first time, can see the transition from stable burning, what before was an explosion, now we have stable burning, convective plumes of burning. This is hydrogen burning, helium burning into higher and higher elements. And not only that, we can even zoom more and more and more to get to resolve for the first time the transition from stable burning to a detonation. So this is really cool because it also gives validity to all the type 1a supernova simulations with unresolved ignitions. But it also allows us to study pretty interesting physics. So I'll show it again with a better perspective of scale. If I can, again, come on, next slide, please. I need to have the mouse in my laptop for it to work. So this is same simulation, but now with the Earth for scale, which is pretty cool. The Earth is really useful for white dwarfs because they have really similar sizes to white dwarfs. So as you can see, the carbon-aged white dwarf is slightly larger than the Earth. And the resolutions that we managed to resolve, so the stable burning region is comparable basically to half of Europe, more or less. And the region where it detonates, if we zoom in, is pretty much comparable basically to Leuven, I think, a bit larger than Leuven. Yeah, more or less. So in this region, we have cell sizes of around 50, 60 meters, so you can just basically see individual houses, more or less. So somebody pointed out at a certain point that this has a better resolution than weather forecast predictions, and I believe that, to be honest. And yeah, so the thing is, turns out, like, we did this just to check if this could be done, and it could be done. And afterwards, we have learned that this not only is the first time that these detonations have been resolved in 3D in an astrophysical context, but apparently also in terrestrial physics context. We don't know if this is just because there is a lot of secrecy with regard to nuclear explosions, and maybe in Los Alamos they have 3D simulations of this, but there is nothing open access for studying the transition from stable burning to detonation. So we're using this simulation to study that. So this is where we get into detonation physics that are a bit more boring, but at least we have a couple of more movies. So for example, this is a close-up of the come on, open the movie, please. Where's my movie? Oh, it's here. No, it's not here. Okay, it's not opening. Okay, I hope if I click here, we have the choppy version of it. So for example, this is a close-up of the detonation region that I shouldn't have chosen a black background for this projector, I guess. But so this is a close-up of the detonation region, and we have enough resolution that we can just take cells in this direction. This is the direction where the detonation is going to form. So in this area, we just select cells. As you can see, we have so many cells that we can have 1D profiles and compare how the transition takes place with 1D simulations, for example. So we can see how the pressure and density, this is pressure and temperature, how the profile steepens until it forms a detonation. And we can compare this to analytical and 1D models, which is what we are currently doing in the paper that we are about to submit, where we studied, among all the astrophysical aspects of it, we studied also detonation physics. I don't want to bother everyone with this, but apparently this seems to match some 1D idea of how this takes place, which is called a Seldovich gradient mechanism. And what we have found is that analyzing this thing is in 3D is much more complicated than 1D because you have all the weird shapes. But this also, again, gives validity to type 1a supernova simulation, which is super important. And the other thing that we have been doing with this, you can probe so many physics with this, that we have been studying the nuclear reactions, the nucleosynthesis. Well, I'll let it run, I don't care. The nuclear reactions that lead to triggering the explosion itself. So at the beginning, we had full helium in the surface. So naively, one would expect that you just go through this alpha ladder, just triple alpha, you go into carbon, you do alpha capture of carbon, and do oxygen, and so on, and so on, and so on, and this will lead to the runaway. But what we have found is that there is a crazy bottleneck in this reaction. The alpha capture of carbon is super slow. So you start piling up. It would be nice to have the movie stopped at a certain point, but so at the beginning, you start piling up carbon. Come on, can I get just one more frame? Okay, whatever, yes. So you start producing carbon. The moment you have, you have a pileup of carbon, the moment you have any oxygen, it burns super quickly through the rest of the elements, and it goes up the alpha chain. But carbon, it's really slow to get rid of. But this all changes the moment you start having any free protons. In our simulation, we had a really simplified initial composition, so we didn't have any protons or anything in there. But when we reach this level in the alpha chain, we start having side reactions that release proton. And the moment you have protons, what we have found is that you have this, what I call proton-catalyzed reaction, that I don't know if it's the right term or not, because I'm not an expert on this. But these protons start being captured by the carbon that you have been piling up and producing nitrogen-13, which is really efficiently capturing alpha and goes to oxygen, freeing the proton again. So basically, you are doing this reaction to bypass the super slow one, kicking up the detonation itself. So I don't know how relevant it is for anyone in here, but we are warning everyone that works on type 1a supernova to have really realistic initial compositions and broad nuclear networks to account for this, because this seems to kickstart the detonation itself. So yeah, as you can see with this simulation, we can cover physics ranging from astrophysics to nuclear physics. And no, that's pretty much my time perfect. So yes, but the main takeaway point from this simulation is that this it gives validity to all the simulations we have with unresolved detonations, meaning that if you start adding resolution in all the simulations of unresolved explosions, they may be physical. It seems that they still explode. So this has relatively big implication for a type 1a 3D simulation community. But that's pretty much where I'm going to leave it, I think, because it's almost 40 minutes. So as a summary, I've been talking about really random things, as you can see. So from neutron white dwarfs, the summary was that basically we're finally able to start simulating these systems. Their gravitational wave, as gravitational wave mergers, they will be sources in the decihertz range. Their jets will produce very bright electromagnetic transients, but this is just the infancy of this field. For wider mergers, what I want everyone to at least think of is that there's a large unexplored parameter space of wider mergers, and as these mergers can be chaotic, maybe we may have unexplained transients over there, and at least now we know that these low mass mergers could explain some calcium-rich transients. And from the resolved ignition, that we have given validity to type 1a supernova simulations, and the problems are very important. I need to work on what is the takeaway point for this for a broad community, but yeah, that's pretty much it. Thank you very much.
Thank you very much, Javier, for this very interesting talk. Are there any questions? Oh my goodness, yes. I'll start here and work my way down.
Thank you for your talk. It was really interesting and also amazing simulations. First of all, I want to ask you, what's your take on why it's important to add magnetic fields to these simulations? Mm-hmm. Because most of the behavior you showed us is mainly hydrodynamical, in my opinion. Yep. I may be wrong. And also, I'm really interested in, I assume you use a constant adiabatic index?
No, this is all with the Helmholtz equation of state. So we have a proper equation of state. We don't fix the adiabatic index.
Oh, nice. Then could you also expand on how do you get the chemical composition of your simulation? Because it seems really, really nice.
So first, I will address the magnetic fields. I guess where you're coming from, you believe that the behavior is hydrodynamical. Are you talking about the jets in the neutron white dwarf? Yeah. Yeah. Okay. Yeah, I've had a discussion with. Yes. The explosion. In the explosion. Yes. So okay. Just for the record, in all of these white dwarf mergers, we also have magnetic fields, but they don't seem to play a key role in any of the ignition or anything like that. So all the simulations have magnetic fields. And yeah, we don't comment on them too much because in these ones in particular, they don't seem to play a crazy role. If they don't explode, we have observed that they lead to some sort of magnetically driven outflows as well. So you can have some sort of lower power jets if these ones don't explode. To be honest, we are finding a lot of jets with Arepo, so we are starting to get suspicious of whether our MHD implementation is just too prone to producing jets or if they're really physical. In the case, I don't know if you were asking about the case of the neutron white dwarf merger as well or not, because I have had people commenting that if it's 10% the speed of light, it's not really a jet. This is just a disk outflow. This is not that. I mean, it's magnetically driven, but I'm not sure in which direction your question was. So magnetic fields, yeah, go elaborate. I was going to say that the main role that they play, at least in white dwarf mergers, is really efficient angular momentum transport, but they don't have features that I can identify out of the box right now for the white dwarf mergers.
Yeah, my question was more related because typically when you include magnetic fields, you kind of look for Alphen waves or King stabilities or tier mode stabilities. Yes. So, but they are on a lower, even lower time scale.
Yes. So yeah, we have colleagues working a bit on analyzing this. What's this called now? All the instabilities. that trigger the amplification of the magnetic fields and all of that. MRI. I was looking for MRI. I couldn't remember MRI, yes. And it turns out with AREPO it's a bit complicated to analyze because the unstructured mesh makes everything a bit difficult to define. But yeah, in principle, we have checked that at least for the wide ornithostar merger, we resolve enough physical scales to resolve the triggering of the MRI, so they should be fine. But yeah, I'm not completely sure what you mean.
So you think you can explore more MRIs?
Yes, potentially yes.
Okay.
Yes,
and, well, and regarding the other question, like, could you expand a little bit more on how do you get the chemical composition?
Chemical composition. So all the simulations that I have shown today had really ideal initial compositions. So these white-dwarf mergers were initially just pure helium, carbon, and oxygen. Normally, in most simulations nowadays, we add some solar metallicity or a fraction of all the metals. But these ones are, like, I started working on them really at the beginning of my PhD, so they're relatively old. And we had simple helium, carbon, and oxygen. And all these yields are produced by the nuclear burning, because we have the hydrodynamics coupled to a 55 isotope nuclear network in this case. So that's how we obtain all these different isotopes through nuclear burning. And then for all the spectra, we post-process the simulations with an even larger nuclear network to obtain more accurate values. So we trace the temperature density in the simulation over the entire duration of the simulation and post-process this with a larger nuclear network for obtaining the yields.
Sorry, I have more questions regarding the numerical methods, but I want to discuss that later.
Okay, we can discuss this offline.
Thank you. Thank you for the really nice talk.
Yes, sir.
Can you talk a little bit about how you set the ignition scale?
The ignition scale.
Yeah, I don't know a lot about ignition. I would think it's not scale-free, but I would think it's a kind of thing where you could just keep zooming in and find a point where the ignition starts. Why is it, you had 1 centimeter, for example, for one of them. What sets that?
I may try to go for 1 centimeter one day, but so the whole thing, the way I did this one basically was I knew where the detonation is going to trigger because we had this simulation with an unresolved ignition, and AREPO is almost perfectly Lagrangian, so I knew what trajectory at a certain point. I was like, okay, I know this is where the detonation is going to explode. I know this is the trajectory that the region, the gas that is going to explode is going to follow. So I think this was like 5-6 seconds before explosion, which for these time scales it's fine. I started increasing resolution around this trajectory and run the simulation. Then we saw this. Basically, that's why I have two. If you look at it, I have 2 levels of. Come on. Okay, I'm gonna open it externally. So that's why I had 2 levels of refinement in the end. On top of the standard AREPO resolution. So basically, I ran the simulation with this resolution. Come on. And this led to a still unresolved detonation. Like we saw the burning, which was already an improvement. We could see, and instead of just having helium, helium, helium explosion, now we have convective burning, but it was exploding on a really small scale, and we couldn't see it. So, but I found where it explodes, and I did the same thing again. And that's what we kept. So I rolled back the simulation, basically, and add another criteria, which is, okay, in this region that is going to follow the region that explodes, add resolution way before it explodes. So that's what we see here. We're even zooming more and more and more. This region now has a even higher resolution because here I knew is where it was going to explode. So this was the procedure. It was pre-iterative. In principle, I could just go 1 level more and resolve more, but it's already pretty expensive. It can get more and more and more expensive. But in principle, with this method, you could just go higher and higher resolution. The limitation is timescales in the end.
Yeah. But then how do you choose a number like 1 centimeter? Where does that come from? If it's a turbulent activity and that's, it's self-similar at all scales, how do you choose a scale?
So well, you mean how did I choose it in AREPO or?
Well, you're saying this is like unresolved. It looks pretty resolved, but I mean,
sure.
How do you decide?
No, this is resolved now.
Resolved?
So, well, yeah, that's a good question. So in principle, the thing is, there were 1D simulations saying, okay, you need, in order to have certain number of cells for a width of the detonation shock, you need at least this special resolution. Like the width of the shock is going to be this spatial scale. So that's what I went for. And here we had looked at the conditions for the detonation. How does it compare to 1D? Like, okay, for this density and temperature in 1D, they find that you need around 100 meters of cell size to be able to resolve it. So I was like, okay, make everything 50 meters in here. So that's what I was doing. And then the detonation itself, we are measuring in this other movie. Can I go to the next one? This really is not obeying me today. In this one, we were, for example, the analysis that we were performing in this case was literally that, like checking how many cells do we have in the shock front, do we have enough resolution or not. So even in the worst case, we still have like 10 to, okay, now it's left the unresolved, the resolved region, but when it starts to trigger the self-steepening, when it's at this point, we still have up to around 5-10 cells in the region in 1D. Around five cells for the shock front where most of the burning takes place, which is basically the limit of resolving it, I would say.
Thank you.
I don't know if it answered the question correctly, no, but we
Okay, more questions. Hi, thanks for the really cool talk. I was wondering about what your thoughts are on like the types of assumptions you have to make to get these computations to run in a manageable amount of time, like which ones in particular maybe that you are worried about, and if you think that in the next 20, 30 years that we will have any technological advances that will increase what we can do in 3D.
So, yeah, that's a good question. So for white dwarfs, this is I think this is pretty good. Like we are in a good position because now our EPO is purely CPU, but we're working on implementing this on GPU as well. So far, I think we almost have working already the nuclear reactions already on a GPU to sideload that load. So that would speed things up a lot because for these simulations with nuclear reactions, in particular in this one that you have so many cells where the burning is taking place, that's most of the computational cost. So if we get to port our repo to GPUs, in principle, we may increase quite a bit the speed in this. In fact, there is an Repo 2 version now going on that works substantially faster. But for the field of white neutron stars, it's not that simple because the fundamental problem that you have there is that numerically, you have a relationship between temporal and spatial scales. So if you need to resolve things very small, you also need extremely small time steps. So even if you speed things up a lot, nothing is going to help you if you need to do 10 billion time steps. You still have to go through 10 billion time steps. So only if the CPU frequencies were going up instead of the core count, this would help, but it's not going in that direction. So in that sense, I don't think we're going to see too much progress in that regard. This code scales really well, so we can add more and more and more cores and run faster, but at the same time, the number of time steps, it's what it is. So if you can parallelize it, but the time steps are in series, so you cannot go more fast than that. So I don't know. It will be better, but I'm not sure. Depending on the field, for things with similar sizes, we will go better. For things with different sizes, I don't expect that much progress in coming years. I will try. We have to talk about it. Yes. I think maybe, yes. We run in the same problem as with neutron stars, but I think, yeah.
Hi, super nice talk. For the system that's not supposed to ignite but does ignite, I was curious about the orbital configuration that you choose and how realistic is it or not, and yeah, the motivation to.
So the motivation for well, I'm not sure, where am I? Oh God, well, I almost closed the presentation entirely. The motivation for this one was initially was my project on the first year of the PhD, which was to study gravitational wave release of common envelopes. So this was really, that's why we were looking at it initially as a common envelope event. We were choosing to simulate, so I was post-processing 3D image simulations of common envelopes to obtain gravitational waves, and we had simulations of a successful common envelope ejection where you have the orbit shrinking and eventually they stop. And we observed how would this be detectable with LISA, where do we land? And then we also started to study, okay, but what if it doesn't? And we didn't have a proper simulation of a failed common envelope ejection, or where the core and the companion merge. So this was meant to be the final stage of such an event, when you have the core and the companion really close to each other, and then we're the final stage, when they're about to merge. So that's the initial condition that we had initially. So this is just, we initially placed them at like 3 times the distance of Rorschach overflow in this one, I think. And this is engulfed in a, well, this was helium pseudo-vacuum. Like we looked at the densities that you would have close to the core of the red giant core and put this, the vacuum around it. And yeah, we have to artificially shrink the orbit a bit until they start doing mass transfer, because otherwise, if you put them exactly at the point of Rorschach overflow or a bit far away, the merger will eventually take place, but it will take place in timescales that we just cannot simulate in 3D. So we have to put them a bit closer than that. So that's the main caveat that the simulations have. I think it's not going to dramatically affect the result, because in the end, maybe you have a more stripped core by the time that they start merging themselves, but I think the outcome is not going to dramatically change. So that's the main caveat of the initial conditions that we have, but we have that problem with all 3D simulations in general.
Really nice work. I have a couple of quick questions. So first, about the calcium-rich transients. There's this other double detonation scenario, right, where you have massive enough carbon-oxygen white dwarfs, which if they accumulate enough helium on them, and the same thing can happen, that the helium ignites and
yes.
So can you differentiate between, say, this scenario and that scenario observationally? Is that something that is...
Yes, in principle, yes. So, well, unless this can be triggered the same way, which I don't believe so, the most standard scenario for subtransaccharide detonations is that you have a carbon-oxygen white dwarf engulfed in a helium shell. You start accreting helium into that helium shell, and that triggers to this double detonation, right? But for that, you need really much higher carbon-oxygen white dwarf masses, because why this was so unexpected is that in order to trigger the detonation of helium, you need really high densities and temperature. And for that, you need a much more massive carbon-oxygen white dwarf. So this only detonates because we have these inhomogeneities in the accretion flow. Otherwise, if you just keep this stable accreting helium for a long time, this will never ignite. So this is only ignited dynamically after the merger. So this is the main physical difference between the two of them. Observationally, the difference will be that this mechanism, the other mechanism only works for really massive carbon-oxygen white dwarfs, and that will lead to much higher production of nickel, which will produce much brighter light curves. So this is going to be much fainter in general. And this mechanism, from my simulations, I've tested different masses. If I go to much higher masses, closer to type 1a, I have tried up to 0.8 solar masses, not 0.9, but with 0.8 solar masses, for example, the tidal forces are so much stronger because you have a more compact carbon-oxygen white dwarf that you disrupt this blob, you don't really form a blob, and you don't really get to ignite, for example. Okay. So this is really dynamical and difficult to predict, but observationally, the main difference is going to be that this produces way less nickel and it's going to be fainter. Okay. The spectra should be relatively similar. Maybe you have much more helium in these ones.
Okay, thanks. And my second, again, quick question is about observations of some accreting white dwarfs. So there are these systems called AMCVNs, which are white dwarfs in a very short period binary, so less than an hour, accreting helium-rich material, potentially from another white dwarf. So you have this accretion phase that is prolonged enough. Can that be accounted for in these, like when does it happen, when does it not happen? Because they are also considered progenitors of type 1a supernovae.
So it could be the main challenge is always igniting the helium shell, right? Like I think the moment you have a helium ignition, you can potentially, there are some papers recently stating that almost all carbon-oxygen white dwarfs can support a double detonation if you have a strong helium shell around them. The question is igniting the helium. So if we can get, the problem is this mechanism only works after the disruption. So we need mergers. I think if we would have this system, we could observe this system during the stable mass transfer stage, or even at the beginning where we're just transferring mass faintly, there would be no way of telling if after it merges explodes or not, unless it merges, I think. I'm not sure.
Okay, I think unfortunately we've run out of time, but Javier is around for the rest of the day. So if we can thank Javier again for his talk. Thank you all for coming, and there is no seminar next week because it's a holiday. So have a nice day off.